After specialization topic is slope stabilization using piles. When slopes are unstable, soil can slide off, and when this volume of mobilized soil is large, the damage can be very costly. Slope failure causes an average of 25 to 50 deaths each year and costs $1.8 billion in damages. Soil instability can be caused by many factors, but in general it is the result of reduced shear strength within the soil. On a natural slope, slip surfaces often form where landslides, valley rebounds, or tectonic shifts have occurred in the past. Shear strength declines in these locations because the prior movement reduces the slide resistance of the soil. Other factors that can cause an increase in slope instability include removal of support through erosion or excavation, overloading by natural or man-made activities, and other factors in the soil itself, such as its composition, structure, and stratification. The topics I'm covering in this video include the theory of pile stabilization and the various types of piles used in this application. Slope stability is based primarily on the factor of safety with respect to the shear strength of the soil, which is the ratio of the shear strength of the soil to the actual shear stress on the soil due to the applied loads. The shear strength is affected by properties of the soil such as the cohesion and internal friction angle of the soil and the normal stress at the point of failure. The desired factor of safety when strengthening a slope is at least 1.5. The mechanics behind the theory of stabilizing slopes with piles involves the resistance of the pile to the overturning moment created by mobilized soil. When the weak soil begins to move, a lateral force is applied to the pile. This causes an overturning moment on the pile. By embedding the pile in stable earth or bedrock, a resisting moment is created. This resisting moment is designed to be higher than the overturning moment caused by the sliding soil mass, which is determined by the force of the soil mass above the shear failure surface. The location of the maximum loading on the pile depends on the strength of the soils included in the slope. When the shear strength of the failing soil is much lower than that of the surrounding soils, the load will be applied to the pile close to the shear zone. But if the stable soil is stronger than the sliding mass soil, which is usually the case, the maximum bending moment in the pile will occur within the stable mass. Typical types of piles used for slope stabilization include drilled shafts, micropiles, and plate piles. Soil nailing is another related method of stabilization which will be discussed. Drilled shafts are cast-in-place concrete piles which are poured into a bored cylindrical hole. This process is shown in the figures on the right side of the screen. They are usually large with diameters of 3 to 12 feet. Because of their large size, the use of this type of pile can often eliminate the need for pile groups and pile caps, which can make it a more economical method of stabilization. The size of the shaft also provides increased lateral force resistance against sliding soil masses. Drilled shafts are often used in urban environments and near highways because the holes can be bored directly into an existing slope without the need to purchase extra right-of-way. This type of pile is also very sensitive to soil conditions. If the soil is completely dry, a hole can be bored and concrete can be poured directly into it. However, if the soil is loose or contains any water, some type of form, either a steel casing or a slurry mix, must be used to support the sides while concrete is pumped into the hole. Micropiles, as seen in the picture below, are smaller in diameter than other types of piles, usually 5 to 12 inches in diameter. They are typically made with a high-strength steel casing. They are a type of replacement pile, meaning that the ground is drilled prior to the installation of the pile. The pictures on the right side of the screen show the installation process. Micropiles have many benefits, such as low vibration during installation, which allows them to be used close to structures. They can also be placed in the ground at any angle, which makes it easy to avoid underground obstructions and karst geology. Unlike drilled shafts, micropile installation is not dependent on soil conditions. Another difference is that the steel in micropiles provides most of the resistance to sliding rather than the concrete. Plate piles were invented recently in 2003. They consist simply of a steel angle and a steel rectangular plate. Since the angle is relatively short at only 6 feet, this type of pile is used for shallow failure surfaces, typically between 3 and 4 feet below the surface. Typical methods for stabilizing this type of shallow slope include replacement of the soil with stone, use of geosynthetic materials, or reduction of the slope gradient. While these methods are often successful, the use of plate piles can reduce the cost of slope stabilization up to 90%. Plate piles are driven into the slope using a vibratory hammer attachment on an excavator as shown to the right. They are arranged in an offset grid pattern as shown here. Soil nailing is another type of slope stabilization. While soil nailing is not exactly the same as pile stabilization, it is still a related topic because the theory behind the method is similar. Rather than a vertical pile placed in the ground, soil nailing is done by placing steel bars into soil at a slight angle from the horizontal, typically 10 to 20 degrees. They are usually installed in a grid pattern with 4 to 6 foot spacing between each bar. Soil nails can either be driven directly into a slope or grouted into a pre-drilled hole, as shown in the pictures to the right. After the soil nails are installed, the soil and ends of the bars are covered with a concrete facing. Soil nailing has many benefits, including minimal disruption of the surrounding environment and structures, small equipment for installation, which allows them to be installed in tight locations, and easy modification of original designs in case underground obstructions are encountered. That's the end of my video.